So for my project, I did nanomaterials and energy storage. So basically, anything that's going to be involved with batteries or supercapacitors. In this presentation, I focus mainly on batteries. And it's going to be mostly, it has mostly to do with the electrodes in the batteries. Today's energy storage devices don't meet requirements for current applications. I'll get to some of those numbers on the next slide here. But as a growing civilization, we are looking for better ways to store the energy that we produce, whether that be through non-renewable resources or renewable, such as solar and wind. And we need things that will take us, or that we can use in not just the home, but in electric vehicles, in our mobile devices. And so that's what I'm focusing on here. This is kind of the progression I'm going to go down. So here's some of the numbers. You can see that up there at the top, that's a screenshot from energy.gov. And this is some of their goals that they're aiming for. So they want to basically reduce the cost. I'm not sure what the exact cost is currently, but they want to get the cost of vehicle batteries to be less than $100 per kilowatt hour, and ultimately down to $80 per kilowatt hour. They want to increase the range of electric vehicles to 300 miles. And currently, I think Tesla, in their latest model, let me see, that's actually going to be in the next slide. They're almost there. They're nearly at the 300-mile range. You can see on, I can do this here. It's going to work for me. No? All right, well, I'll come over here. So this one is showing different types of batteries, and it's from 2011, but you can see the projections here. So this is for lithium-ion batteries, which is what we use in our mobile devices, laptops, phones. I believe Tesla is actually using lithium-ion in their cars. Currently, lithium-ion batteries range from 195 to 220 watt-hours per kilogram, and the theoretical is roughly 320. I don't know the exact number on that. And so we've got a ways to go. You can see 220 up to 300 something, and they're projected to get there by last year. So we're not quite there yet, but we're working on it. Nickel metal hydride, which is not actually, here is it? Oh no, it is here. So we're way down here in roughly 100, and they don't really know its potential. But those are the two of the most common batteries with high discharge rate and decent capacities. Yeah, okay. So the driving force, like I said, is going to be electric vehicles, energy for the home, and the devices that we have. Tesla has developed their electric vehicles around lithium-ion batteries. They've developed their own. Their Model X has a range of 237 miles up to 289 miles. And last year they unveiled their semi-truck for cargo transportation. And the cheapest one has a range of 300 miles, but their long-distance one has a range up to 500 miles. The only issue is the batteries are bulky and heavy. They take up space, and that kind of costs them money because they can't carry as much stuff. And so we're looking on ways to reduce the size and weight of the batteries so that these things can carry a lot more. Down here at the bottom, it's a kind of a quote from an energy website. I don't remember which one, or it was a news article. California produced way more electricity than their grid can handle in January, February, and March last year. And so they had to sell some of it to Arizona and Nevada and stuff like that so that they didn't overload their grid. And if they had a decent storage solution, something that didn't take up too much space and could handle, heavy usage days, which can range up to 20 times the normal electricity usage, they wouldn't have had to sell their electricity. They could have just stored it and used it later on. And we can see one of the issues with batteries here is their energy densities, a specific energy and energy density don't really compare to combustible fossil fuels. The ones that we use most of, the fossil fuels that we use most are methane or natural gas in the home, diesel, and gasoline in our vehicles. And you can see they're about up to a magnitude of times more energy dense than batteries. You can see that the lithium-ion batteries that we have go up to 2.63 megajoules per liter, or 0.36 to 0.875 megajoules per kilogram. And gasoline, methane, diesel, 46.4, 48, and 55.5 megajoules per kilogram. So you can see that we don't really compare when it comes to natural gas and fossil fuels. So that's why we haven't switched from non-renewable to renewable yet. So what we're using today, mostly nickel cadmium, nickel metal hydride, and those are expensive. That's the issue with those. The cadmium and the metal hydride are both expensive materials to produce, and you can see that this is just showing you kind of their chemistries and how they operate on the inside. They're dangerous, so anything basically with lithium ion, lithium polymer, they tried to develop a pure lithium electrode battery, and it was just too reactive and they couldn't get it to work. They can explode. Another issue with a lot of batteries is electrode degradation. That's why you get a limited number of cycles. You know, I think up to 1,000 is something that we see commonly. And that's because in lithium batteries, you get these dendrites forming here. So basically what happens is when you recharge the battery, the lithium ions have to come back across from the cathode to the anode. And when they do, they can build up these dendrites that can pierce through the separator and cause a short. And that can lead to kind of another Note 7 fiasco that we saw a few years back. They're bulky and heavy, and they can be toxic. So that bottom picture there is a lithium-ion battery compared to a lead-acid battery, which you commonly see in vehicles. And the lithium-ion battery is about half the size and a fourth of the weight for the same voltage and capacity. And toxic, we have a lot of, I don't know, people that vape or whatever use lithium cobalt batteries. And those are pretty dangerous because while they can put out a lot of current, they heat up and they go into thermal runaway, they can explode. If they get damaged, they can explode, stuff like that. So they're just dangerous and toxic, and you don't want to mess with them. So the first thing I'm going to cover is the carbon nanotubes here, or carbon nanotubules, excuse me. Basically what they did is they used a chemical vapor deposition process to put carbon nanotubes into a porous aluminum membrane. And on top of that, they used iron catalyzed reaction to put smaller nanotubes into those tubules. So you can see the picture on the left, that's at the 1 micrometer scale. And that's the initial porous membrane from the carbon nanotubules in the aluminum structure. And on the right is a 50 nanometer scale, or it's on the nanometer scale. And that's a picture of inside those tubules from the left. So what that did was it increased the capacity of intercalation. I don't know if y'all know what intercalation is. It's just basically when the ions from the cathode, or from the anode cross through the battery and get basically embedded into the cathode. And so this increased the intercalation capacity by almost 2 times. They tested the initial porous membrane with the carbon tubules, and then they also tested after that the tube-in tube, which is what you see on the right there. And what that is, it was a 2 times increase in intercalation capacity and up to possibly or more 980 milliamp hours per gram. So that's a pretty significant increase for lithium batteries as far as capacity goes. The next thing is viral structured templates. And what they did here is they created a solution of a virus called tobacco mosaic virus, which was mutated with a cysteine molecule in the, I believe, the first position. And what they did with this is when the viruses were, there was a special process that they used to put these in an ordered structure onto a gold, on a gold structure, or a gold surface. And that's what the picture here on the right is showing. So you've got the TMV1 cis is what they abbreviated that to. And it's mounted on a gold surface. And then what they did from there is they used a plating solution to put, I think what they used was platinum, but they could have used just about any metal they wanted. And what that did is it increased the conductivity and the overall surface area. And I'll show a picture of that in the next slide. It's super cheap and super efficient. As little as 450 milligrams of the actual virus. It could coat a whole square meter of the gold surface. It's very customizable, so what they use here is a helical structure, but it can be adjusted and tweaked so that you can use it for other structures and shapes and stuff. Like I said, it has a high surface area, and it had about a 2-fold increase in capacity over the non-templated electrodes. And you'll see why in the next slide. So this here, or I guess in A there, that's the nickel-coated surface without the virus-structured materials. And B is a cobalt-coated surface without the virus-structured surface. And then you can see the increase in surface area from the bottom there. Those are the same things. C is nickel-coated and D is cobalt-coated, but they are structured with TMV1 cis at a concentration of 1 milligram per liter. And it's just a drastic increase in surface area for use as electrodes. The test results from this, so you can see in the top graph there, that's going to be the number of cycles versus the capacity, or the capacity versus number of cycles. So the bottom lighter gray dots show the non-TMV1 cis-coated surfaces, and the darker dots show the TMV1 cis-coated structures. And it's pretty apparent that the overall capacity, even from the very beginning, was greatly increased due to the coating with the virus. And the bottom one here is the voltage versus the capacity over, was that 2 cycles, 15 cycles, and 30 cycles. So the dotted lines are uncoated and the solid lines are coated. And you see after about 30 cycles, it stabilizes at about a 2 times increase in capacity with the virus. All right. And the last thing I want to go over here is the fuel layer graphene and aluminum ion batteries. So this is kind of a 2-in-1 kind of deal. You have the fuel layer graphene used as the electrodes in a new chemistry, which is aluminum ion. Stanford, I think, was leading this in 2015, and they developed one, and it was pretty incredible what they achieved. But what I wanted to talk about here is that with the fuel layer graphene, again, it's a chemical vapor deposition process. And they found that using 4 to 5 layers of graphene saw the best diffusivity of ions into the electrode. And what that means is basically the ions can pass through and get all the way into the electrode and not be inhibited. So you got greater capacity and discharge current. And that's something different than we see in normal batteries because they use bulk graphite electrodes and the diffusivity in those is just terrible because you've got a giant chunk of graphite and so you only get ions intercalating in a few layers of that graphite. But with this, they intercalate and you get a great increase in capacity. In a Raman spectroscopic study, they tested this particular battery, and they saw that with 1,000 cycles, there was no loss in performance of the battery, so no decrease in capacity. The people that actually did produce this battery tested it up to 7,500 cycles and saw a current density up to 5,000 milliamp hours per gram and there was no loss in capacity over those 7,500 cycles. You can see, oh yeah, okay, so this graph on the bottom left is showing you the current capacity over the range of cycles, and you can see that the discharge current, which is the red, or discharge capacity, and the black squares, which is the charge capacity, remains pretty constant over the course of 1,000 cycles. And the efficiency, which is that top green line there, stayed pretty much flat across those 1,000 cycles, which is a good indicator that obviously there was no loss in capacity. And this is a great example of what we could possibly use in the future for electric vehicles and off-grid solutions for home energy. And I believe that is all.
Question.
How does the virus impact the surface area?
I'll go ahead and go back here. Right there. Okay, so what they did is that they used magnetic fields to orient them. And you can see, so here, this is kind of how they structure themselves with their proteins. Mm-hmm. And so it's a helical, it just kind of spirals up. And so in the magnetic field, they orient straight up and down. So you've got these giant structures perpendicular to this flat built surface. And what that does is it creates an effective area, or surface area, that's not just this flat part, but all the way up and down these structures here. Because these are coated in conductive metal. So it's like a forest. If you have a, you know. I could go on with it if you want to.
Can you go forward to your graphene one?
This one?
Uh-huh. Mm-hmm. So what's the difference between A, B, and C there? Is that just number of layers of graphene, or they modify it somehow, or?
Yeah, I should have remembered that. I wish I could tell you. I think what I was just trying to show here is how it increases the surface area and diffusivity of the ions into the material.
Okay.
It just shows the porosity of it so that the electrolyte can get in there and let the ions transfer.
Gotcha. Interesting. All right, thanks, sir. You guys could get me your evaluations. Good.
I was looking at my PowerPoint, and I think I'm going to end up having to get rid of some of those examples because I feel like it's just too long.
It's gonna be too long. Okay.
Yeah. Are you?
That's fine.
Okay.
So long as you're kind of hitting the minimum time,
Yeah.
you can certainly take some stuff out if you feel like you're gonna be running long.
Yeah, it's just I really want to explain what the experiment is doing, and that was the biggest problem that I had when I was explaining it to you before because I had so much to talk about and
Right.
the little time.
Hey.
Hey.
Yeah, that's fine.
Thank you.
How's it going?
Hey, you found all my papers.
Yeah, I forget that maybe they were yours.
Because they were all organometallic.
Yeah, it was like I had a 50-50 shot. Probably more like the prints were really it's more like a 90% shot.
Yeah. He probably also has a printer that works, so maybe 100 too.
We could steal the one out of one phone.
Yeah.
Seriously, because it's slusher.